How come phi k is of the form phi j implying phi I? How come you made that assumption?
Where are you talking about? Case A, perhaps?
Case 3A, yeah. You said suppose without the loss of generality.
Yes, I'm just trying to. So we're applying rule 1 here. So rule 1, right? This is saying if you've got some phi and you've got some phi errors psi, then rule 1 says we conclude psi, right, over here. So this is what I've got here. I've got in my proof that phi I follows from 2 earlier statements by an application of rule 1. So it better be that phi I looks like this psi, and then one of these two looks like phi, and one of these looks like phi errors psi. So that's all I'm saying here. I'm just saying let K be the one that looks like an implication. So it has to be.
K is the one with an implication. Does it have to be bigger than J? Does it have to follow after the statement of phi j?
No. It's just that they just have to be both occur earlier in the list than I. Doesn't matter which order they occur in up here. Doesn't matter which order they occur in up here. It's just that phi I, so somewhere earlier on the list, we have phi j arrows phi I, right? And also somewhere earlier on the list, we have phi j. Maybe these are here and here. So then I can conclude later on in the list, by modus ponens, rule 1, phi I is legitimate.
Okay, that makes sense. Thank you.
Yeah, is it okay? All right. Anything else? Okay, a theory is deductively closed if for any sentence phi of the language, if from the assumptions T I can prove phi, then actually phi is in T already. Right? So if I use these as hypotheses, I don't prove anything new. And 2b just says the deductive closure of a theory of a theory T is just the smallest superset which is deductively closed. So in fact, the deductive closure of a theory is just everything you can deduce from these hypotheses T here. Right? Let T be a theory. We say T prime is an axiomatization. This is not the same T prime as 2b. T prime is an axiomatization of T if for all sentences phi Again, so theories are about sentences rather than formulae. Right? So if T, single line here, if T prime proves phi, if and only if T proves phi. Now, this is only going to be interesting if there's something interesting about T prime, because according to this definition, T is an axiomatization of itself, right? Which is rather uninteresting. But maybe T prime is finite. So it's finitely axiomatizable if I can find a finite T prime. If there's an axiomatization of T, there's an axiomatization T prime of T with T prime finite. It might be that we've got a countable set of sentences, but we don't need all of those. We can actually find maybe a finite subset or a different finite set of sentences which have the same conclusions, in which case we say T is finitely axiomatizable. And going back to a definition from the earlier part of the course, 147, say theory is complete theory T is complete if for every L sentence, sigma, either T proves sigma or its opposite. Actually, it turns out that complete theories are, well, somewhat rarer, right? Rather than the opposite here. Let me just look at some examples here. This is page 72. That's okay, the theory of groups, we define that to be the deductive closure, everything you can prove from the group axioms. Well, there are only 3 axioms here. So we could say already, the theory of groups is finitely axiomatizable. We only need 3 axioms to deduce everything about what's true in all groups, right? So the soundness theorem will say whatever we deduce from the group axioms will be true in all groups. A group is just something by definition in which the 3 axioms are true. The soundness theorem guarantees that anything we can prove from the axioms using predicate calculus will also be true in all groups. But the theory of groups is not complete, because in some groups, the commutative axiom is true, and in other groups, the commutative axiom is false. So the statement that every pair of elements commutes under the group operation, that sentence can't be provable from the group axioms, and nor is its negation provable from the group axioms. Because if either one of these were provable from the group axioms by the soundness theorem, it will be true in all groups, which it isn't. Okay, and so it's not complete, not a complete theory. And what we have here are then just a list of other kind of mathematical examples, right, here, of different kinds of structure. If I just think of a language which just has a symbol R, which is 2 place, and you can think of it as a kind of a less than symbol here. the theory of dense linear orders without endpoints is everything you can deduce from the sentences in this exercise, right? Here. Actually, you can show that this is complete, though that takes a theorem, that's a harder theorem to prove, right? What else do we have here? Theory of graphs. A graph is just a set with a symmetric relation on it, right? If I think of it as a graph without the links on the graph are not arrowed, right? They're just lines, segments. So this just says it's symmetric. If V1 is connected to V2, V2 is connected to V1, right? Here. I can take something like the reals with an ordering on it. That's an ordered field. So those axioms give us the theory of ordered fields. I look at everything that's provable from those axioms. But again, there's only finitely many axioms there. So I'd say that this theory is finitely axiomatizable. Okay, since there are only finitely many, actually we can just take the conjunction of those axioms and just make them into one sentence, right? If we wanted. Not that there's any particular use for that at this stage. Right? Okay, so let's just see quickly one example. I realize that time is up here. Here are the groups. The theory of groups where all elements have order less than some fixed p. Right? So what that means is if I apply the group operation, for some number of times to any object, right, there's going to be some power of that object. I've applied n times, say, to that object, and I get back to the identity element. So the order of an element is the least n, such that applying the group operation, you get back to the identity element, if it exists. So the theory of groups, where all the elements of order less than some fixed p, right, is then saying, okay, for any object in the group, either it's got order 1 or order 2, order 3, or order p minus 1 here. So here is an axiom that will ensure, when added to the group axiom, that the group has got all of its elements of order less than p. Okay, so let's call that a day here. Do look at these other examples that are here on this on the list. Yeah, and I'll be setting some questions from the exercises for next week, which are there on the next page, which I'll email out to you.